While learning differential geometry, you know that one important concept that emerges is geodesic. Now, the question is that, is geodesic at all an abstract mathematical concept, or can you physically construct a geodesic? Is it possible that through simple practical experiment at home, you create a geodesic and then find out some of the remarkable features of this so-called mathematical abstract concept? Why particles follow a geodesic? Isn't it great that you create a geodesic with your own hand and then see the geodesic equation, which no more seems to be monstrous but seems to be a very easy understanding feature? In this video, I'm going to show you a practical demonstration of creating a geodesic, thereby revealing some of its extraordinary powerful feature, which is going to make your concept much stronger. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to part 3 in our learning of this series of learning differential geometry. Now, before I go ahead in constructing and show you practically what is a geodesic, here is a quick recap on the earlier lessons in case you have missed. Now, in the first 1 and 2, that is the 2 lessons, what we looked is basically the nature of space. What is a curved space? What is a flat space? What is absence of curvature? What is differential geometry? And even we saw some Sanskrit shlokas which actually reveals Pythagoras' theorem and various other things. So how the nature of space evolved with the passage of time, we have seen into some of our earlier videos. We have also looked into what is called a spherical geometry, which is very important. What was the history and how the spherical geometry evolved, how the mariners navigate the ocean and astronomers watch the sky. So what is so new and what is so new about this non-Euclidean geometry? And we also looked into what are called the spherical axioms. We looked into a very unfortunate but a very interesting story of what is called the great mathematician and geometer Janus Bolyai. Now, if you want to go through the earlier lessons, I have given it in the I button and in the link also. So just to tell you that Janus Bolyai was born in 1802 and he independently developed the concept of non-Euclidean geometry, and that is something remarkable. But what happened is that most of his work went unrecognized because he discovered that Carl Friedrich Gauss, which was not true, had discovered similar ideas on non-Euclidean geometry, and that was basically a kind of a tussle between his father Farkas Bolyai. It's a very interesting history, a story which you can read through my earlier lessons. And he became increasingly isolated and became paranoid, dying in relative obscurity in 1860. We also looked in the earlier lesson, which is called the angular excess of a spherical triangle. That is a measure of how much the sum of its interior angle exceeds 180 degrees, which is the usual convention of a Euclidean triangle. And in a spherical triangle, the sum of the interior angles is always greater than 180 degrees. What we looked also in what is called the Girard's theorem, which relates to spherical geometry and provides a way to calculate the area of a spherical triangle. The theorem states that the area of a spherical triangle on the surface of a sphere is equal to the sphere's radius squared multiplied by the triangle's angular excess. We also looked into what is called a geodesic triangle, which form the shortest paths between 3 points on a curved surface, such as a sphere. So these shortest paths, as we will see further, are called geodesics, and on a sphere the geodesics are segments of great circles, and the sides of geodesic triangles are thus arcs of these great circles. We also looked into what is called geometry on curved surfaces, which is too detailed to explain the recap, and some of the features and what is the difference between intrinsic and extrinsic geometry. Now that was basically a quick recap of the first 2 lessons, and now we come to the idea of constructing geodesics. Now, before I go ahead, just to make the viewers a kind of a note that I'm going to construct a geodesic because I want to make sure that the geodesic equation, which you will later learn in differential geometry, does not comes to be something difficult, monstrous, too detailed, too difficult. So first, let us construct a geodesic with some practical experiments and then look into it. So till now what we know is that the shortest path between 2 points on a flat space, for example these 2 points, is this one. So by definition we know that on a curved surface geodesics are equivalent, I would say, the curves which represent the shortest between 2 points. Now as you can see that when we talk of a geodesic, immediately on a spherical mode it comes that the great circle. Now, as we say that geodesics are equivalent, I mean to say the curves that represent the shortest distance, so obviously that is straight. I mean to say the straight line joining the 2 points. So obviously the question comes that what is straightness? And this is very central and important in understanding geodesics. Now you see that in geodesics, straightness actually does not refer to what do we mean by straight line in a Euclidean space. Rather we try to say that something which minimizes the local curvature. That means if I take a curved surface and I have to go around here, that would be minimized. So from here we can say that the concept of straightness allows us to define geodesics intrinsically. So remember that geodesic is the curve. But as we call straightness, that means it minimizes the local curvature. That means as minimum as it gets. So because in analogy it becomes simpler to say that it is straightness, so it feels straightest as you travel, almost like a straight line. Now here is a bead, right, and this is a kind of a curved surface. Now you see if I move this bridge slowly up and down and up and down and again, I wish I would have made the animations in loop. So what it tells is that the bead would not feel itself constantly turning or deviating, rather it would experience the smoothest possible path. So the bead won't say or it won't feel the curvature. It would experience the smoothest possible path just like a straight line. So that is why we call it as straightness. Because straightness is not a perfectly straight line, but it minimizes the local curvature and it says that you feel straight. You feel as if you're going on a Euclidean space. Now, just as the bead would not feel it is constantly turning, it would feel the smoothest path that it is traveling. Geodesics actually leads us to 2 important characteristics. And we are going to explain those characteristics so that the learning becomes better. The first one is that they provide the shortest route, obviously, the 2 points that are not too far apart. And the second one is that they provide the straightest route between these paths. That means the straightest one. Now, when we say that what is straightness, we need to define what is straightness. Now, in order to define that, first I would like to ask you a question. Rather, I would say that you yourself ask these questions. Do you think these concepts, for example geodesics particularly, are purely mathematical? Do you think that these are purely abstract concepts and has nothing to do with the practical life? Do you think that it cannot be constructed in practice or at home or using some instruments? Then you are wrong. These are not abstract mathematical concepts. These are something which can be constructed. And for that, I would like to make use of this yellow summer squash, or in India it is called kaddu, and somehow it looks like this. And this amazing fruit, I would say this amazing structure of the fruit is going to make your life easy. It is going to reveal you something great. Now, I would like to mention also that the most of the books that you would read in differential geometry, they do not pay attention in such practical matters. They would straight away go to the equation. And it is perhaps for this reason that the construction that we will describe over here now won't be something which you can find in most of the books. However, I have taken a part of this construction from what is called Visual Differential Geometry by Tristram Needham. And I would urge you significantly to explore the ideas by all means. Theoretical contemplation, you can draw, you can use computer simulation, but please do it with your own hand. So what I want you that you go to a local fruit and vegetable shop, and you can supply with this what is called this amazing fruit. This looks like a yellow squash, right? And it looks like a yellow summer squash. Now first step would be to construct a geodesic, that means a straight line, by stretching a string over its curved surface, which would be something like this. I cannot show the animation in hand. I will make later a video or a YouTube shorts. So on a fruit vegetable, something like this, construct a geodesic by stretching a string over its surface. Once you have done that, use a pen, something like this black one, to trace the path of the string, and then you can remove the string. That means you have drawn a mark. Now you can make a shallow incision on either side and close to the inked path, and then use a vegetable peeler. So let us make a shallow incision, something like this. That means you're cutting the vegetable around that path. And then you are using a vegetable peeler to remove that narrow strip or peel between the two cuts. I cannot show you right now, but I will demonstrate further. Now peel the strip of, place the strip of peel flat, this one which you have, place it on the table, and then you observe something great. The geodesic within the peeled strip has transformed into a straight line on the plane. So this is how you do or construct a geodesic. So you take a fruit, you make a string, then you trace the path, then you make a shallow incision, you remove that shallow incision, and then place it on a table, and you will see that it actually shows a geodesic, that is, it has formed a straight line on the plane. Now the question is why? But we will come to that. But before that, I would like to show you demonstration one by one. So this is the, So you see, this is the longer one, the black, and the straight line is the shortest. So what would be the step number 1? So here is the step number 1. What you do is that construct a geodesic by stretching its string over. Second, what you do is that use a pen to trace the path of the string. Then step 3, here it shows you can peel off or use a knife or a vegetable peeler to remove the narrow strip, and then you can put it over here, and this red arrow shows that it is nothing but a straight line. Now in order to understand this, first let us be clear with certain significant points. The point is that this one, that although the strip is free to bend in the direction, that means perpendicular to the surface, it remains rigid if we try to bend it sidewise. Here it is. Again, let me show you. It remains rigid in order to move it sidewise. That means tangent to the surface. Now here I am going to employ something which is called a proof by contradiction. That means I will start with a negative one, and then it will come to a positive one. And let us imagine that what would happen. So suppose we will assume that such a peeled geodesic did not become a straight line when it laid on the table. So here it is, and suppose it is not a straight line. So let us suppose there exists a geodesic path when peeled and laid flat on the table, and this is something which does not become a straight line. So what it will happen? I mean to say, we assume that it is not a straight line, and then we will try to make it a straight line. That is proof by contradiction. So we will first of all, what we will do is that, as you can see, this shows the longer path, this one shows the shorter path, and this one shows the shortest, that is the straight line. So the shortest route, I mean to say this picture, the shortest route between the ends of this dotted, I mean to say the non-straight line, remember it is the dotted one, that is the non-straight line plane curve, is the straight line which is connecting them. That means, as illustrated, this is the path of the true geodesics. We already found using the strong, but let us pretend that you don't know it for now. Although we have collected, but let us pretend that you do not know for now. So we may shorten the curve, right? We may shorten the curve by deforming it slightly towards the straight shortest route, which will yield the solid path along the edge of the peeled strip. So if I try to deform it, this gives a solid path. I'm trying to deform, so just try to imagine this kind of thought experiment that you're trying to deform it, and this gives us the solid path that runs the edge of the peel strip. And therefore, after you reattach that strip, so after deforming it, after you reattach the strip to the surface, that means this one which you see now, this one I have shown it earlier, so it would be the peel strip which you're attaching, reattaching it. So when you reattach the strip of the surface, the solid curve provides a shorter route. Here is the solid curve which provides a shorter route over the surface than the dotted one. That the dotted one is the blue one. So if you reattach that, that will provide what is called a shorter route over the surface than the dotted one, which we had supposed to be the shortest, and this is a contradiction, and we have proved our assertion. So this is what we called proof by contradiction. So if you really want to go back, you can do that. So here is the shortest route between them. I should have shown this one later. And then you pretend that the true geodesic we already found you do not know. Then you see that we can make the dotted curve by slightly deforming it, and this gives the solid path. And if you reattach the strip to the solid surface of the solid curve, it provides a shorter route over the surface of the dotted one, which was supposed to be, and that is what we have proved by contradiction. So let me show you step by step again with a simple diagram. Suppose that this illustrated dotted path is a geodesic, and there's a narrow white strip surrounding it which does not become a straight line. This results to this. So we can shrink that. We can shrink the dotted path in the plane towards the shortest straight route in the plane, thereby producing the solid path, which is this one. And this is the longer, this is the shorter, this is the shortest. And then when we then reattach the strip to the surface to this solid path, it is still shorter than the original dotted path. So when you reattach that, it actually shows that the solid path is still shorter than the original path, which was supposed to be the shortest path, which is not. And this one is the shortest path. So the solid path is still shorter than the original, which was the dotted path. And that is what we prove by contradiction. So which was supposed to be the shortest path is no more. Now this is something which is remarkable, and from here I can say we can conclude a kind of a theorem, and the theorem says this: if a narrow strip, say for example G or F or whatever, of a geodesic is cut out from a surface, that is the fruit that we are constructing, and laid flat on the plane, then that straight peel of fruit cut becomes what is called a straight line. That it becomes a straight line, and that is what is called a geodesic. Now here comes something extremely remarkable and extremely important. Now I would want you to go back to step number 3. That is when we are taking out the curve, we are taking out the peel from that fruit or from that curved surface. So imagine that we are reattaching the strip to the curved surface instead. So what we are doing, we are reattaching to the strip. And this is the strip. So I have just magnified this one, and you can just imagine. So we are reattaching this on the fruit, and you can just ignore what is the history and how we got to the point. And we have just picked a narrow straight strip, and we have unrolled it back. We have unrolled it back onto the surface of the channel. That means the channel that we have cut, and let us see what it happens. So here is something remarkable. So here is a peel which is cut up. Here is the narrow peel, and this is what we are trying to posit. So we have unrolled it back onto the surface into the nano channel. So the result is this: this shallow channel need not exist. That means even if the shallow channel which we have cut through the knife, if does not exist, the surface decides where the strip must go as we unroll it. And this is something very, very fundamental and very, very important in our understanding. The surface decides where the strip will go and where will it unroll. This gives us two important features. The surface is important. It dictates the path of the strip, not the shallow path or the shallow channel. And also this means the strip conforms to the shape and contours of the surface naturally. So this natural thing is what we are going to take up when we proceed in today's video. Remember that even if the shallow channel did not exist, the surface itself will tell the strip where to follow and unroll. This means that the strip conforms to the shape and contours of the surface naturally. So from here what we find is that this was the earlier theorem, isn't it? From here we got into this, that the shallow channel, if it does not exist, even the surface will tell well to unroll. And from here we get to the next theorem or next point, that in order to construct a geodesic on a surface, you can start from a point in a direction, say for example V, stick one end of the length of a narrow sticky tape down to P, unroll it onto the surface starting in the direction. And that is why I call it, it is a time reverse converse. That means whatever we have done in the first part, that is a narrow strip surrounding it becomes a straight line. If you reverse that through time, then again you can construct a geodesic. But in this time, the geodesic or the peeling of that line is actually does not depend on a shallow channel, but the surface or the curve will itself tells that where it will unroll, where it will fall, and where it will lead to. Don't you think this is remarkable? And this actually creates what is called, I would say, a geometry which is not dependent on a frame of reference, a geometry which is free, a geometry which does not depend upon any coordinate. Let me show you further in the next part. So here it was, we further formed it into this, and then we formed into this, and we show by proof by contradiction that rather than the dotted line, the solid path is the shorter. And also we tried to peel that line, and from there we got the peeling part, and when we move it over here. So this is the peeled line. For example, this is the surface of the fruit which you have cut it, and when you are trying to put it over here, forget about this channel, you can even put it over here and it will take a shape of kind of this. Also I can take that fruit, that yellow squash summer fruit, and I can create a geodesic over this. So that means it tells that when we reattach the strip, the surface will decide where the strip will go. So here you can see that when I am reattaching over here, I am not following the shallow channel, but still it creates a path. I am reattaching over here, I am not following the shallow channel, it creates a path. So the surface decides where the strip will go. And this brings us to the final point, that why do objects follow geodesics in space-time? This will incredibly show you, and you will be able to understand in the easiest possible fashion, why do objects follow geodesic in space-time, coming up into the next part of the video. So if I try to put this strip, that is the peeled one, over here, isn't it? Then I am not following the shallow channel. That means I can create it here, here, or here. Similarly, if I follow this fruit, I can create a geodesic over here. I can create a geodesic over here. I can create a geodesic over here. That means I'm not following the shallow channel. Very few important features comes up. Number one is this. This actually challenges our intuition, because you are expecting to follow a predefined groove where the strip belongs. But the inherent properties of the curved surface actually shows where the strip will unfold or where it will unroll. Also, this shows that the importance of intrinsic properties or intrinsic curvature. That means the shape of the strip when it unrolls is dictated by the curvature, not by pre-existing marking or channels. That means it is a coordinate-free geometry. Also, the shallow channel created by unrolling the strip might be a hint for a geodesic. So geodesics are the straightest possible paths on a curved surface. As the strip unrolls, it follows the minimal local curvature, potentially aligning with a geodesic, and we say that nature is very lazy. And that is why it follows the straightest possible paths. And this brings us to this kind of an understanding, that if there are 2 points and I'm shining a light, it would go straight. But if I space, in the absence of mass, photons will travel. But in the presence of sun, In the presence of sun, what will happen? That it will create a curvature. Why? Because the sun is heavy. So now you see what happens. This light photon will create or show a geodesic path. Again, it is not again because of the presence of that shallow line. It is because of the curved surface which is created due to the nature of the curvature it follows. So the photon takes the path of a geodesic that appears to be curved, and curvature is due to the presence of mass, and that is the beauty of general relativity and the photons or the deflecting of the starlight. So the gravity has already created the curvature, but the geodesic is following because it will automatically follow that, and that is what the fruit example has shown. Further, you can see that if I go a little bit technical, then the sectional, I would say the sectional curvature also shows the same. It would follow a straight line with no deviation. This one, the sectional curvature would be less than 0, and here the sectional curvature will be more than 0 because it will follow a different path. And in terms of general relativity, only if I shove the ball straight, then what will happen? The sectional curvature is 0, so Ricci curvature is 0. The size of the ball remains the same. Here by the point size, I means the differential size or differential volume. Here what happens? Here it has got a positive curvature because the geodesics are converging, and here you will see that the size of the ball is decreasing because the sectional curvature is more than 0. And what happens in this kind of a scenario? You see the sectional curvature and the ball is increasing in size. The size of the ball increases because Ricci curvature is less than 0, and this is sectional curvature is also less than 0. So the geodesic concept, or the movement of particles, either in general relativity or whatsoever, it takes this shape because it is independent of coordinate. It doesn't have to take that path, but if you can place that peel on that fruit, it will take any kind of a shape depending on the curvature. So here you see again two people of different, starting from the poles, they are meeting at a point, and this is also the same, that the shape of the ball, it changes. So that is what is called the Ricci tensor, and the ball shrinks as it moves, meaning that it is a positive curvature. So from here, as I am again showing you, this white line actually shows that you don't have to follow the shallow path. So objects with no external forces will follow the straightest possible paths in curved geometry, and we say that is why nature is lazy. The shape and properties of the surface itself will dictate where the strip will unroll. And in general relativity, geodesics are the straightest possible paths in curved space or time, and that is why the starlight bending has a very big resemblance about geodesics, because just as the strip follows the natural curvature of the surface, objects in space-time also follow geodesics because that is the natural path dictated by the curvature of space-time. And in general relativity, objects in free fall follow geodesics, and that is why I call it as natural. Natural means that it will follow as dictated. You see further few important points. That crucial observation is that the channel does not exist beforehand. That means coordinate free geometry. Also, this is a key point in general relativity because there is no predefined tracks, which I was telling, and this analogy determines the geodesics, where objects actually follow due to the absence of external forces. So here now you can see here, if I put this on a curved surface, the curved surface represents the space-time warped by gravity, and the last line is very important. Objects follow geodesics because they are simply moving along the natural paths within the curved geometry. If you go back to today's video, you will see I showed you when I'm peeling that fruit and I'm putting it over, it is following a natural path. So finally we can tell this analogy refers to what is called the equivalence principle of relativity, with no external force follow geodesics, where objects with no external forces follow geodesics, not because of pulling force but due to the inherent nature or the inherent curvature of space-time. That means if I'm peeling off that fruit part, again if I lay it on the fruit, I need not necessarily have to follow that channel. The curvature itself will tell you where the fruit is landing, And that is the beauty of the curvature, and that is what Einstein's general relativity tells, that the analogy reflects the equivalence principle. What is the equivalence principle? It tells that where objects with no external forces only follow geodesics, not because of any pull or push, but due to the inherent curvature of space-time. So today we have learned the creation of geodesics. Go to a nearby fruit shop, get hold of this kind of a weird structure, peel it over, put it on a straight path, and then put it on your table. You will see it is a straight line. Then again try to reattach it. You will see that it will take its own shape due to the curvature of the surface. So that's all for today's video. Thank you very much for taking your time and watching this video. Please do subscribe if you have liked by clicking on the subscribe button and hit on the bell icon to get all the notification from Physics for Students. Please do write to me for any confusion in this email ID, and you can like and subscribe to my other channel, General Relativity Explained, where I put up videos primarily only related to general relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. So please do let me know how did you like the video by putting up further comments, and Physics for Students will be back again with more interesting and surprising video on physics and mathematics. But till then, may the good Lord be with you.